Let's get going. Okay, so once again, I'm employed at Columbia. Received several grants to develop Stan, seeking additional grants, still seeking to use Stan for business purposes. And some of the stuff that we're going to talk about today, a little bit from last Thursday, a little bit from next Thursday, pertains to the stuff that businesses really prioritize a lot, at least in principle. Some of them are using Stan, most of them are not. But the things that businesses are particularly interested in is predictive performance of models rather than estimating a treatment effect, testing a hypothesis about whether the consumers adhere to this or that model of consumer behavior, etc. Really, all the emphasis is on ability to predict things and to make decisions, business decisions based on those predictions. Now, like I said, most of them are not using Stan, but this is one reason why these things come together, and Columbia has policies on this sort of thing that you wouldn't want to encourage researchers to overstate the case for software that's developed for research grants that are administered by Columbia, in an attempt to get more customers or clients or whatever. And so that is why these conflicts of interest have to be disclosed. So to pick up where we left off last time, this is actually estimating the same model that we were using before, using a data set on political economy risk to model the black market exchange rate premium for a bunch of countries a long time ago. That can be estimated by a linear model. You can either use the R-squared prior, which is what Stan_LM forces you to do, or you can use Stan_GLM with family equal Gaussian, and you're using the same likelihood, but Stan_GLM allows you to use different sorts of priors that are placed directly on the coefficients rather than putting prior on the R-squared. So normal priors, student T priors, there are several options for prior families that our StanArm supports. However, all of those make the assumption that your priors on whatever they are independent. So you're really only specifying a marginal prior distribution rather than a joint prior distribution. It's not as if anyone thinks that is a correct thing to do. Your beliefs about the parameters should be should be characterized by a joint distribution rather than merely a marginal distribution. However, many people, including the vast majority of our StanArm users, have very strong difficulties specifying a joint distribution for pretty much anything. And it can be like pulling teeth to even specify any information such as a marginal distribution. That's one of the reasons why when you use Stan_GLM and some of the other functions to specify QR equal true, if you're not going to change the default priors, that at least makes the predictors orthogonal to each other. And so maybe a marginal prior distribution on those is not the worst thing in the world. Anyway, you can estimate models that are as simple as this one with little difficulty in, well, at least obtaining the posterior distribution is of little difficulty with our StanArm. But whether that is a good posterior distribution, how to make sense of it, etc., are all additional questions, and the answers in this particular case are kind of pessimistic. But anyway, you can use the Shiny Stan R package like we talked about on Thursday to look at And also to save a lot of plots. I don't think I talked about that specifically on Thursday, but when you generate those plots, there's going to be like a little icon somewhere over on the left that asks if you want to just save this plot as a RDS file, and then you can load it up later in a different R session even in R, and it's just one of these ggplot objects that is basically an algorithm for how to render itself onto the screen. So you can save those, you can dump them back into the R process you're currently using, etc. But all of that is interactive. And so today, at least the first part of the day, I want to focus on generating plots programmatically that you could put in a R Markdown file or a paper or something like that. Or if you knew you wanted to generate a whole bunch of them, you could just write down the code for that and they would be created automatically. So the first, the Bayes plot package is another R package, and it's maintained by Jonah Gabry, who we were talking about last time, former QMSS student. The Bayes plot package isn't specifically, or most of it is not specifically for MCMC output that is created by Stan, but it works especially well for MCMC output created by Stan, because MCMC output created by Stan tends to be very good, at least from a computational point of view. The draws tend to have a small amount of dependence from one to the next, and so you can pretty much analyze them as if they were independent draws. So all these functions that start with PPC are intended to be used for posterior predictive checks after you've obtained the posterior distribution of all of the unknown coefficients and standard deviations of errors and things like that, generating predictions and evaluating how well those predictions line up with the data that you have available. And there's a whole bunch of them here that you can read through the documentation on. We will go through a few of them, but they basically work in pretty much the same way. If you're using them directly, and all these functions can also be used as we get farther along in the semester, and you're writing your own Stan programs to estimate models that go beyond what our Stan arm can do, all of these functions in the Bayes plot package will basically accept as their first argument either a matrix of posterior draws, a matrix of posterior predictions, something like that, or an array thereof. If you have multiple chains, which is always advisable, you can just use as.array to make that into an array of posterior draws, and then the functions that distinguish from one chain to the next, not so much these, but another set of functions we'll talk about in a second. And you can see plots that have different colors for different chains and so forth, help to diagnose the usual fact that they converge to the same distribution with the default arguments. So a lot of the more diagnostic ones start with MCMC underscore. They work like the other ones. They take a matrix or an array as their first argument. Again, you have a lot of choices for plots you can use. Some of these are more useful than others, but basically all of the plots that you see in Shiny Stan have equivalent versions that are just in the Bayes plot package and can be generated programmatically or even just by typing at the end. So the most basic plot, or the one if you just call plot, it's I think calling MCMC underscore DENS for density in the Bayes plot package, and you get a visual representation that goes a fair bit beyond but includes all the information that if you just did print of post. So if you do print, you see the posterior median and something about the posterior standard deviation. If you do summary, you see, you know, numerical values for the 25th and 75th percent quantiles, etc. But visualizing as a graph is good because it emphasizes the fact that there's an entire posterior distribution of all these unknowns given the known data that you have underlying everything that we do when we're doing a Bayesian analysis. And so this is a plot of the marginal posterior distributions in kind of a squished format. The blue circle is a posterior median, the value such that there's a 0.5 probability that the true parameter is less than this, a 0.5 probability the true parameter is greater than this, and these are the same posterior medians that are printed out on the screen when you do print post. But this also captures the 50% credible interval. That's the dark blue lines there, and probably a 90% credible interval that is extended out to the edges of the blue line. So, you know, for something like this one here, that dummy variable, you can say that there's a less than 10% chance that the coefficient on this is positive, given that 90%, probably more, well more, of the marginal posterior distribution on the coefficient for this variable is in negative territory. And so these probability statements are something that people, particularly if they don't have a whole lot of training in statistics or not, you know, good training, really like to hear. So if you're, you know, really interested in like this parameter, that parameter, something like that, to be able to say, well, there's a 2% chance under the model that this parameter is positive or negative, whatever, is a, you know, really nice thing to hear for someone who's, you know, worried about, are we using the wrong sign as a result of our estimates compared to what it really is. And so you can make, in the Bayesian approach, probabilistic statements about parameters. They describe your beliefs about those parameters, whereas technically speaking, from a frequentist perspective, you can't make any probability statements at all about parameters because parameters are not random variables. And so you can only make probability statements about your estimator of the parameters. So you can say, you know, something like, if we did this over and over again, our confidence interval estimator would capture the true parameter 90% of the time, but we don't know what the true parameter is, which is, you know, sort of the kind of the ultimate thing of interest for a lot of these studies. So being able to make probabilistic statements about parameters or about hypotheses is a really natural way of approaching, you know, empirical research that a lot of people think it has to be, or it should be that way always, without realizing that the probability statements that come from frequentist estimators pertain to the probability of something entirely different that they probably don't care that much about. Similarly, well, not really similarly, but along the same lines, a lot of the stuff that falls under the heading of sort of introduction to moderately advanced supervised learning also does not yield probability distributions. You would not really get posterior medians, but you would just get circles that don't have, you know, any necessary interpretation as being part of or some aspect of a posterior distribution, and moreover, you don't get uncertainty intervals. And so there's no way to say, well, if you predict something in held out data, what's the probability that the thing that you're predicting is positive or negative? That's not something that you're going to get, at least no way to get a Bayesian posterior probability for that statement without actually doing the Bayesian analysis. And so a lot of people, talk about, well, Bayesian approach, getting these posterior distributions, it's slow, it's memory intensive, all sorts of other things compared to other ways of using a computer. And people like that tend not to recognize that the answers provided by these different computational techniques, they're answering different questions. And so the MCMC, or the stands implementation of MCMC, is not slow just because it's wasting time, or it's implemented inefficiently. For the most part, it is implemented pretty efficiently from a computational perspective, but it takes a lot more time because it's doing a lot more work in order to try to get an entire posterior distribution. And every realization from that posterior distribution has the appropriate probability, even out at the tails and stuff like this. And so it's a much more ambitious technique, and it's trying to provide a much more nuanced answer than the more limited approaches that a lot of the deterministic algorithms are yielding. And consequently, it's not correct to interpret those things as yielding a posterior distribution. And that ought to be obvious for anything that just yields like 1 point. And there's no, entire distribution there. And so posterior distributions are great. They reflect our uncertainty about everything. That uncertainty should be taken into account when making any sort of a risky decision. And the Bayesian approach, and pretty much only the Bayesian approach, yields that sort of thing. And so if you actually take the time to obtain that answer, it's sort of, cringeworthy to see people who, spend all this time to get a real like Bayesian posterior distribution and then don't show the distribution. They just, talk about the, posterior medians or the posterior means or something like that, as if they were doing, a frequentist analysis or maybe some sort of supervised learning thing where the only things that come out are points. Sebastian. Becca.
Oh, yeah.
Oh, Sebastian again.
Okay, sorry. So if you assume, are we assuming in these posteriors that the distribution of the possible values of a single estimate is normal? Or are we assuming that they're having?
No. So it may very well not be normal, and we're going to see, well, those look pretty normal, but the next ones we're going to see are puffed up. So this is kind of, if you're looking straight down on the distribution, so you don't really see the height, but you see the concentration a little bit. So no, there's no assumption that the posterior distribution is normal.
So that seems like very different. That seems like if it was totally normal, you could train normal.
Yes.
You could summarize it.
Right. If it was normal, you could summarize the joint distribution with a mean vector and a covariance matrix. That's, again, but marginally you could summarize it with just a mean and a standard deviation. Yes, and that's all that this is attempting to do. But a lot of times things will look more normal marginally than they are jointly. And so you kind of have to investigate the bivariate or trivariate plots to see this sort of non-normal dependence in your beliefs about these parameters. Becca?
These are all standardized. Right?
No. You just can't see the axis. There you go.
Oh. Okay. So if you had some coefficient that was like growing
100
inches or something.
Yeah,
like
it would really throw off the scale of this. Yeah. Well, no, you shouldn't scale, but you should probably make two different plots. One that includes the one that's like way over here, and then one that excludes it. There's an extra argument to plot where you can say what to include and what to exclude.
You just make them like
well, you shouldn't, but you could z-score the predictors.
Yeah.
That doesn't necessarily mean the coefficients are going to have any particular relationship to each other. And so with Stan, you could scale your predictors by constants, but you shouldn't do anything else to them because that at best will be redundant and at worst will confuse Stan or not confuse Stan, but confuse our Stan arm, which is doing a lot of this stuff internally and then undoing it at the end to get posterior distribution in the units with respect to the raw parameters. And so if you're doing all these like complicated, centering and rescaling and orthogonalizing to your predictors on the outside, then you have to remember to do the same thing when you're predicting with the other predictors for a posterior predictive distribution. It's just a way where you can easily trip yourself up. So by all means, rescale dollars into thousands of dollars or something that is more reasonable to interpret. But you shouldn't be doing a whole lot of other stuff. Sure.
So those are posterior distribution.
Yes. We also have a R squared and a sigma, but all the ones up here are coefficients. And there's an intercept.
And they come from like a joint distribution that MCMC.
A joint distribution that MCMC has drawn from. Yes.
And it just like is able to calculate that really quickly on this.
Right. So once you have the draws, calculating the median is pretty straightforward. Calculating the interquartile range is pretty straightforward. Calculating the 0.9 and the 0.1 quantile for this and that is pretty straightforward. And so making this whole thing is pretty straightforward.
So is it just like integrating joint distribution?
No. So there's no analytical integration going on. You just get all these draws. You get 4,000 by about 12 matrix, and just column wise, what's the median? Column wise, what's the interquartile range? Column wise, what's the 10th percent quantile and the 90% quantile? So you're really just doing operations on numbers at that point, and you can summarize a margin of the posterior distribution with a graph like this just by connecting up the lines and putting on the dots. Salif.
So the way, like what this is representing is just our beliefs, the posterior belief.
Marginal, yeah.
Yeah, we don't still know how this actually relates to the real parameter that is out there.
Right. I, in general, want to probably discourage people from thinking about how well does this capture the true parameter, because we're only going to know that in simulations. Now, if you do simulations, the Bayesian thing tends to, capture the true parameter pretty well. But in any actual research, we're not going to know what the true parameter is. And so I think a better way of thinking about something like this when you estimate it on wild data is that you would be irrational for believing about the parameter anything other than what is represented by this, provided that you genuinely, put what you believe into the prior distributions that went into the model in the first place. So if you did this for, somebody else's beliefs, then obviously this is what you think they should believe. But in any event, it's more like what would it be rational to believe given the information that you have, rather than does this capture some true thing that, we're not going to know anyway. Other questions? Okay. So, yeah, this one, it doesn't really show the extent or the lack thereof to which these marginal distributions are normal. Sometimes they kind of are, oftentimes they're not, and that's okay. we can take a non-normal distribution and still describe its median and its interquartile range and a bunch of other things. If its tails are not super heavy, we can describe its posterior mean and variance and other things like that that are technically, integrals. But anyway, here's an example of using the MCMC areas function in the base plot package. It takes a matrix rather than r_stan_arm object, but you can coerce a r_stan_arm stan reg object to the underlying matrix that's S by K or whatever draws just by doing as.matrix on it. Here I specify a regular expression for which coefficients I want to see plotted. So we can see like this. This one kind of looks normal, although it has sort of long tails. We have a posterior median. We have an interquartile range, from here to there. But it actually shows the whole distribution. But you have, stuff like this doesn't really look normal. In the next version of base plot, you can put MC_areas_ridges, and it will kind of squish this up and give it some perspective, so it kind of looks like a mountain range. Anyway, you can visualize more margins in less space when you do that. It looks pretty cool. So that's that. Like I said, these are just plots of the margins. It's fairly easy to obtain plots of the bivariate margins, so the distribution marginally among any pair of variables in your posterior distribution. Here I plot these. I forget what PRSC exactly stands for, but these are a bunch of dummy variables that pertain to the same categorical factor. I guess there's 5 of them. And the 6th category is the reference category. Anyway, we can see basically scatter plots here of draws for any pair. You can see that these are positively correlated, which is not surprising considering they're dummy variables that pertain to the same factor. There's nothing wrong with there being correlations in the posterior distribution. It simply means your beliefs about these coefficients are positively correlated, or your uncertainty about these parameters is positively correlated, etc. These look extraordinarily similar, but so along the diagonal you have marginal histograms. Above the diagonal and below the diagonal you have bivariate plots. The difference between the above diagonal and the below diagonal, you do this with Stan, or r_stan_arm, is the ones above the diagonal affect or reflect draws from the posterior distribution that had an above median probability of being accepted. So in the ones below the diagonal, they had a below median probability of being accepted. But you can see they look almost exactly the same in this, in which case it's saying there's a lot of compression in the probability of any particular footprint of the Hamiltonian Monte Carlo process being accepted. And that's good, but sometimes when you're trying to diagnose problems, it can be good to separate those out. Also, in this case, I used the default actually, and so there were no divergences or transitions that exceeded the maximum tree depth or anything like that. But if they were, they would be plotted in different colors: red for divergent transitions, yellow for transitions that exceed the maximum tree depth, etc. And so you can see a little bit where in the posterior distribution Stan was having trouble drawing from the posterior distribution correctly. And usually you have to look in 2 or 3 dimensions to see why the posterior distribution is difficult for Stan. If you're just looking at 1 dimension marginally, that usually isn't very illuminating, because Stan if all the margins of the posterior distribution were independent, that never happens. But if it did, Stan would have no trouble at all drawing efficiently from that distribution because it doesn't really have to worry about the dependence among the parameters. It's only when you have sort of weird, extreme, non-constant dependence between, you know, one parameter and the next, particularly as it relates to a like error standard deviation or something like that, that things can get a little bit more difficult. That for Stan will still tend to do really well. It just might give you a warning saying you have to increase the adapt delta in order to get this right. I need to go slower through this part of the posterior distribution in order to not miss anything. Anyway, when you get warnings like that, it will often tell you look at the pairs plot to try to figure out what is, you know, going wrong. But usually, even if you figure that out, the answer is just to increase the depth delta a little bit, and things will go well. If that is insufficient, then you need to start thinking about reparameterizing your model. Of course, the parameterizations in Stan are already, or in RStan ARM are already hard coded. So that basically means you have to start working on your own Stan models to get around that. But we'll learn how to do things like that in April. Here is another plot that we saw before or on Thursday, although we saw it in Shiny Stan. This is a little bit harder to see in this version, but we have the dark blue line representing a kernel density of the data, and we have these faint blue lines corresponding to the same kernel density, but for the predictions, the posterior predictions of the data. And you can see the posterior predictions have too little density over here where there's a second mode, too much density like over in here, you know, between the two modes. And so seems to be aspects of this posterior distribution that our model, relatively simple model, is not capturing very well. And so that can often help, you know, in this case, or, you know, a lot of cases, the density of the outcome, you know, sort of corresponds to like poor countries over here and rich countries over there, or something like that, in which case maybe the way in which you've introduced the level of development of the country into the model is, you know, not right, or your data on the level of development for less developed countries is measured with too much error, or, you know, any number of things that can go wrong. You ought to be able to recognize that things are going wrong. Also, it should be pointed out that these plots that are produced by the base plot package or by Shiny Stan, etc., are really just building on the ggplot2 library, which we talked about, those of you who were in the class last semester, how to use. I haven't emphasized ggplot2 that much this semester because not everybody is so familiar with it. The plots that I've done up until today have mostly just been using base graphics, just so that, you know, more people, I guess, would be familiar with them. The ggplot2 graphics are, I think, in a lot of ways better, and you can program with them. So this was an unfortunate choice. But, you know, I outputted, you know, pvcheck, it outputs a ggplot thing, and then I wanted to add a layer or a qualification on it to put the legend at the bottom. Unfortunately, my slides were not big enough, and so you can't really read the legend at the bottom, but oftentimes it looks better at the bottom or the top than over here on the side, which is the default in ggplot. So, Sebastian.
So are the base plots like wrappers for ggplot?
They output.
Or are they just compatible with plots?
They output ggplot objects. So I could add another ggplot statement to it, and it, you know, these ggplot objects are really like R objects that have methods for how to render them. And so when you add layers and qualifications, you change the objects and they get rendered differently. And so you have a lot of flexibility to change how these things look, the thicknesses of the lines, the colors of the line. If you don't like Columbia blue theme, you can change it to, you know, something else with, you know, the usual ggplot2 stuff. So if you're familiar with ggplot2 already, you know, knock yourself out modifying these things. If you're not familiar with ggplot2, it's probably something to look into, but not something that you really need to be overly concerned about this semester. You can just make the default ways of rendering these things, and that would be probably fine. The ggplot2 syntax is a little bit unorthodox from R, so we're not going to dwell on it too much. But if you already know it, you can do pretty much anything with these plots that you could do with any other ggplot2 object. So here's one plot. This one is not very exciting, showing a visualization of the R hats. R hats is a measure of non-convergence. When it's much larger than 1, then that is an indication that the 4 by default chains that you ran didn't go to the same place. And so that if they didn't go to the same place, then that at least some of them have not found the posterior distribution yet with the default number of iterations, or, you know, there's something about this posterior distribution that is making it really difficult for Stan to draw from the posterior distribution correctly. In this case, almost all of the R hats are like slightly less than 1. There's a few that are like 1.001. You'll see various stuff on the internet saying you shouldn't worry if it's, you know, less than 1.05, less than 1.1. I worry if it's like more than 1.01, but it's, you know, that may be a little bit strict. For the models that are estimated by RSNARM, you're very rarely going to have a problem with lack of convergence. When you do, you'll get a warning. But anyway, you can look at these just as easily as you can see the actual numbers. With harder models, then this is something that you might want to worry about more, and always you at least want to check. But for the most part, that shouldn't be a big deal for the regression models that are in RSNARM. Okay, so another way of analyzing how well your model is doing, whether it's overfitting, etc. So we talked about this a little bit maybe last Tuesday. If according to your model, your predictions are such that the ith value of the outcome should fall in a 50% interval with probability 0.5, then if you have, you know, more than a handful of observations, it should be true that about half of the observations fall in those 50% intervals, but that's not guaranteed to be the case. Again, we have a plot that got a little chopped off here, but across the horizontal axis is the range of the y value. And so I'm calling PPC intervals underscore grouped. This takes as its first argument the y, which was the outcome variable that we modeled originally, a S by N matrix of draws in the posterior predictive distribution, the size of the predictive intervals that I want to evaluate, and an optional argument, an additional factor that you can use to stratify the plots. And so here I'm using the quartz variable. This is the observations for which quartz is 0. This is the observations for which quartz is 1. I don't think this is a dummy variable for like the presence of quartz. I think it has something to do with whether the court system in this country is considered to be independent enough from the executive or whatever system of government they have. Anyway, like, you know, independent, or no, not so independent quartz over here, independent quartz over there. And so by putting in this grouping factor that is one of your predictors, you can see how well your model is predicting in, you know, different scenarios. And in this case, it's not all that good either way, but it's good to know that. So the blues are actual observations on Y. The light blue ones here are the median of the posterior predictive distribution for that particular observation, and these intervals constitute 50% of the predictive distribution for that observation. So it should be the case that half fall within, half don't fall within, but of the half that don't fall within, there should be an equal probability that they're too high than they're too low. And so this one over here, where the quartz variable is 0, you know, maybe about 50% or so, probably more, are falling in their 50% intervals. But when we miss, when the predictive intervals don't include the observations they're predicting, there's a pronounced tendency for the intervals to be too low and for the observations to be too high. Not as bad when quartz is 1. Maybe more correct coverage. Kind of hard to see when I cut off the bottom of the graph. But anyway, this might suggest that there's an interaction between the quartz variable and some other predictor that you have or don't have that may yield this sort of differential predictive performance in the cases that have, you know, puppet quartz versus the places that have more independent quartz. Rashika.
We get a distribution for the Y's because when we do the draws, for each draw of the coefficient, we substitute x's.
Right. So we get
4,000 or 2,000.
Yes. So if all of you were in the model, I can get a posterior predictive distribution for Rashika and anyone else because I have a distribution over my unknowns, and I combine or compose my distribution of the unknowns with the known X data that I have on everyone, and the composition of those things yields a predictive distribution for each observation.
So ideally, if it's, then it has to be above, and so the dark blue dots, ideally you want
25% too high, 50% in the middle, 25% too low. I think you had maybe 3 50%.
Yeah.
Okay, you don't want that. Jude.
So, what are you supposed to do? So you suspect that there's an interaction.
Yes.
And you just have to then add the interaction to the modeling again, and then see the graph, and just do that until you get above, below, and 50%.
Yeah, that would be a reasonable strategy, definitely. Nathan, number 1.
I just don't understand how exactly, because you always say like we can't use anything from our posterior to then like go back and change our model. Does that mean the distributions that we believed previously, or the parameters and the
Right.
relationships?
So I wouldn't use it to change your priors on existing variables, but certainly if you might plan out the models you want to estimate in advance, or upon seeing one or some of the plots, it might suggest to you ways in which the model that you were doing was wrong originally. So what I wouldn't do is say, okay, here's my posterior distribution of the R squared under this model, and then under another model, use that median as your prior median for the R squared. That is sort of one, taking a model that you don't really believe in the first place as a result of these posterior predictive checks. And so you might be skeptical as to whether you're really this certain about what the R squared is. But anyway, this R squared is, you know, when you condition on these variables. If you condition on more variables, then it's going to be different. But I would really suggest, you know, going back to your, you know, base specification, and you're going to put, you know, another variable in or take another variable out, make small changes to this rather than, you know, if the results were a lot different, you know, going with the posterior distribution of that as if you sort of knew that going in, which you didn't. Okay, we can see that. We can see pairs. We can see density. Performance is good. Edwards?
You mentioned it, but I forgot. The x-axis there is the number of drops.
I think it's actually, I shouldn't have cut it off, the index of the observation. So this would be like the first observation in the data set that has puppet courts. You could also probably put labels of what their country name is, add that to the ggplot. Sebastian.
This is all deterministic, right? So for my x's, given my x's and, you know, whatever betas we're using this time, there will be a single block and there's no noise.
No. So you multiply the x's by the betas, add that all up, and then there's a draw of the error from whatever distribution you use to fit the data, in this case Gaussian, that yields the prediction. And so, no, these are not deterministic. So we can do what we did a week or so ago and just calculate the calibration numerically. You know, we could do this stratifying by course or not. In this case, I didn't. We just, you know, create the 25th percentile, the 75th percentile by column, which, because it's an S by N matrix, the columns correspond to observations and the order in which they appeared in the data, although observations with missing this on any of the variables are going to get dropped. Anyway, we can then calculate the posterior probability of observed outcome falling within the interquartile range. This, if the model is working correctly, should be about 0.5, given that we're putting 50% intervals. In this case, it's closer to 64.5%. So this model is overfitting a lot more than the Diamonds model that we did, you know, whenever we did the Diamonds model was. Diamonds model was like 52% or something like that. This one, much worse, 64%. And so you can simultaneously overfit the data in this sense and have a bad model that misses important aspects of the distribution because you didn't include, you know, the right interactions or whatever. So you can have a model that is simultaneously overfitting and incomplete. But these are all signs. Not that there's anything really wrong with how Stan drew it. There were no warnings, like the R-hats were good, etc. But it's basically saying this posterior distribution is not particularly believable, even though it ostensibly represents what you should believe upon, you know, seeing the data. But there's a lot of inconsistencies here in this distribution of beliefs. But, you know, you'll often overfit if you just sort of do the supervised learning thing of, you know, condition on everything in the data set that's not the outcome and see what happens. What happens is you will overfit. Got that. Okay. So different perspectives on this idea of prediction. We talked about this maybe a little bit before, but I don't think I did justice to how important an idea it is, or a contrast. So you might ask yourself the question, or some people have asked other people the question, do you want a model that is expected to predict future data well, or a model that actually predicts a particular set of testing data well? And this is a question that, you know, everyone thinks is obvious and well over 90% of people get wrong. But, you know, whether you get it right or wrong, the question seems equally obvious. If you're talking to someone who's wearing a tie, they will sort of, you know, revert to the second one. Well, you want a model that actually predicts well, not a model that is expected to predict well. But no one really cares per se about a model that actually predicts well on a particular subset of data that was held out to be testing data, because that testing data was past data. You already have it. You collected it. It came from the past, not the future. And so the only reason people care about the predictive performance of a model in a testing subset of data is because it suggests, does not imply, but somewhat suggests how the model will perform on actual future data that you haven't collected yet, because that data will only transpire in the future. But a lot of, you know, supervised learning people have found that, well, splitting into training and testing yields models that, or choices for what model is best, that actually predict future data well, when it predicts held out testing data well, or at least better than, you know, trying to evaluate the model only on data that was used to estimate those parameters. But it's really, you know, they're using this held out testing data as a kind of proxy for future data. And future data is what they really want to be able to predict well in the past. And one of the reasons why way more people get this question wrong than get it right is because they're thinking about, you know, do you expect to predict future data well in sort of the colloquial English way of defining an expectation, like I expect the train to be on time, but we're sort of, you know, conditioned to expect that our expectations will not be met by a lot of things in the world, like trains and buses, anything to do with transportation, other people, the government, anything like that. But when we actually talk about an expectation in a statistical or probability sense, that has a very specific definition, you know, the weighted sum over the entire space of the, you know, function multiplied by its PDF. And so by taking the expectation of a random variable, which is what future data is in the present, you're basically averaging over all the things that the future data could be with the corresponding probabilities as weights. And so when you make your model comparison stuff based on expectations of utility functions of future data, the conclusions that you reach are less likely to be at all sensitive to the perhaps arbitrary way in which you divided, you know, training and testing, you know, away from each other. That was just one way of splitting past data, and if you'd split it another way, you could have come up with a different answer. By taking an expectation, this weighted average, you're basically saying, you know, for all types of all things that the future data could be, I'm averaging over that. And so it's kind of like, well, what if you did, you know, every possible split of data into training and testing and average that? That would be something pretty close to what the Bayesian approach gives you pretty much for free by taking expectations of functions of the predictive distribution. And so, you know, whoever is wearing a tie, their next response is, well, if the future data has not arrived yet, how can you possibly take an average over it? Again, reflecting a severe misunderstanding of what probability is. Of course, the future data hasn't arrived yet. That's what makes it a random variable, but we can take expectations of functions of random variables in principle by doing integrals. In practice, those are analytically impossible, but in practice, we can approximate those integrals to arbitrary accuracy with random draws from predictive distributions. And we can do the integral with a Monte Carlo thing. And so that is all entirely doable. Another thing, Bayesians, when doing this model comparison stuff on predictive distribution, are going to tend the vast majority of the time to use what are known as proper scoring rules. Non-Bayesians, the vast majority of the time, are going to use what are known as non-proper or improper scoring rules. So what's the definition of a scoring rule? You can click on this link to see a discussion by Frank Harrell of this in a FDA context. But anyway, a proper scoring rule is one where the utility for predicting well is maximized at the probabilities yielded by the true predictive distribution. And that encourages the analyst or the forecaster to be honest in making these predictions. Conversely, non-proper scoring rules, the utilities you get from them can be maximized by something other than the probabilities from the true probability distribution, which encourages people to lie. But the scoring rules that you tend to see used most, particularly in a more machine learning thing, AUC, anything with an acronym, ROC, proportion of observations classified correctly, all these things, not proper scoring rules. So shouldn't use them. So sort of review a little bit what we talked about last Tuesday, set the stage for the rest of the day today. Going and the reading for today for a paper that's been accepted to be published in Bayesian analysis by a bunch of people who are at Columbia sometimes. Anyway, it's using this idea of Pareto smooth important sampling, leave one out, cross-validation, which I realize is also an acronym, but this is a good acronym. Anyway, so what we need is a utility function, and that function takes in future outcomes and pulls out, it yields some utility that we get from predicting things correctly. And so for Bayesians, that utility function in a predictive context is usually the logarithm of the PDF for the distribution generating the future outcomes. And that's a proper scoring rule. There's a few other proper scoring rules that you'll sometimes see Bayesians use, but probably the most common one and the one that really makes most sense is going to be the one that has to do with the PDF of the distribution that generated the future outcomes. In this case, in log form, so we can sum over it, etc. So we're going to approximate the distribution or our ability to predict the distribution of future outcomes by predicting present outcomes that have been left out when we conditioned on the data to obtain the posterior distribution. Doing this literally would require that we obtain n posterior distributions, one for each observation that could be sequentially left out when we condition on the remaining n-1 observations. That would be at best time consuming, and in practice something would go wrong computationally when doing that so many times. And so we're going to seek weights that map our S posterior draws that condition on all n observations to S posterior draws that only condition on n-1 observations and nullify the influence of the left out observation on the posterior distribution. And those weights, it turns out to be, are proportional to the reciprocal of the likelihood function for the ith observation. And as Rashiga was saying, for each observation, we have like 4,000 draws from the posterior predictive distribution, or we could obtain 4,000 draws from the posterior predictive distribution. So when constructing these weights, we're going to need, S by n of them. We want to evaluate the likelihood for the ith observation across the whole posterior. So we need 4,000 representative draws from that posterior distribution. Those weights are called important sampling weights, and because it's a reciprocal of something that can get, you know, close to 0 in the denominator, those weights can be highly noisy. And so this approach taken literally would only tend to work well when you have a large number of observations, but we can reduce the variance without introducing very much bias at all by replacing the largest 10, 20% of weights, etc., for each observation with predictions, point predictions really, from an auxiliary model that uses a generalized Pareto distribution as the likelihood for these weights. And instead of using the raw weights, you know, for those extreme weight values, use the predictions implied by the model of those weights. That dramatically reduces the variance, doesn't introduce a whole lot of bias, makes it easy to diagnose when you have a problem of some observation is overly influential and the assumptions of this break down. In that case, you could actually leave out 1 or 2 observations, refit the thing, obtain the predictions. But anyway, you don't have to refit this n times. So when you're done with it, the Pareto smooth weights can be used for a lot of things. We talked about a little bit last week to calculate the expected logarithm predictive density, and to say, you know, one model looks like it's better than another on this criterion. And this is actually implemented in one of the diagnostics. So this PBC Lu _ Pitt takes the outcome, a matrix of posterior predictive draws, and this thing called LW, which is the output of the Pareto smooth important sampling process. So you actually pass in the negative of the log likelihood applied by the model. It returns a list. The thing you want are the smooth weights, and then you can pass that to one of the graphs, and you get this thing, which is quantile plot. And so if your model is doing good, then all the observations should line up on a straight 45-degree line. Here you see there's, you know, some pretty deviations from that. It kind of snakes around. Another indication that it's not good. It also gives you the warning that some Pareto values were not so great. In this case, they were only slightly high, so it's not so bad. But you might want to follow the message and look at the details of that. We can make predictive intervals that are smoothed by these weights, and so they're going to have less noise. Now, the predictive distribution seems to be a little bit better, but we're still, you know, have these observations along the bottom, but we're not doing so good. But a more even spread between bad predictions at the top and bad at the bottom by using these weighting mechanisms. So the last couple of minutes, I actually want to get into the reading a little bit. There's a little bit of vocabulary relating to this M regime. So just to review what it says in the reading, M closed means you're taking the perspective that one of the models you estimated is the correct model. It's the true data generating process. You just don't know which. In contrast, the M open perspective means you're assuming that all of your models are wrong. None of them are correct. M completed is something in the middle, in which case you're assuming that none of your models is correct, but you're going to proceed as if exactly one of them is. We'll talk about the M closed thing a little bit more on Thursday. The rest of the class today want to talk about M open and M completed and ways of doing weighted predictions in those scenarios. And so this also relates to something that's pretty popular in the machine learning community, which is called stacking. So you estimate each of your candidate models n times, actually leaving out the ith observation. That can take a while, but it's within the realm of feasibility because, these machine learning techniques tend to go very fast, much faster than MCMC. You then choose weights across the candidate models in order to minimize the weighted squared predictive error for the left out observations. And then once you've solved to get the optimal weights, you then use those weights along with future x's to predict future y's. But the key problem with this approach, like pretty much all the problems with supervised learning, is that you're only getting point predictions and you're like weighting them and stacking them up rather than getting entire predictive distributions. And so you're not getting any measure of the uncertainty in your predictions. And the uncertainty is something that is really important for a lot of loss functions in businesses. And so it's not just important to be like kind of correct on average. It's important to very rarely be very incorrect. So if you're like a hedge fund manager or something like that, yeah, you want to sort of, predict how the stocks are going to be in the future. What you can't have happen is to like not anticipate 2008. Then you just get wiped out. And so it's not just like the central prediction that's relevant. You have to like insure yourself against these horrific ones. And so you need to know the tail behavior and all that stuff. So what's the Bayesian version of stacking? Well, it's pretty directly analogous, just correct. We choose weights over the candidate models to maximize the Pareto smooth importance sampling glue cross-validation predictive density. You can then use these weights to produce average posterior distribution or average predictive distribution. Unfortunately, the Loo package on CRAN doesn't have this implemented yet, but the one on GitHub does. So you can just install it from GitHub temporarily. We can estimate another model where I've taken out the GDP per capita variable and I've reduced my R squared prior a little bit accordingly. You create a list of the log likelihood values for the 2 models or the 12 models, whatever that you're considering. Make a list with that many elements. Pass that list of log likelihoods to the model underscore weights function, and it does all the calculations that were talked about in the reading for today. It solves that optimization problem from the Bayesian perspective, and it tells you that the weights that you would want to use to average these 2 models together, whether you're doing prediction or whatever, would be to put a 0.84 weight on the second model and a 0.16 weight on the first model. Now that doesn't mean the second model is like true with probability 0.84 and the first model is true with 0.16. It just means using these weights yields like optimal predictions if these are the 2 models being averaged. And so this is a measure of a prediction process where you can get sort of better predictions from an ensemble of models than you might from any one model by putting like all the weight on model 2 and none of the weight on model 1, which is the sort of more typical thing that machine learning people sort of do. They do all this stuff and then they sort of decide like this one model is better than all the other ones, and so we're just going to go with the predictions from this one when really there's just like that much difference between some model and another one, and it would make more sense to average. But what it would have made even more sense is to average distributions rather than averaging particular point numbers without any sense of the uncertainty or the tails or anything like that. Anyway, we'll talk about enclosed things, ways of comparing different models, ways of choosing a few predictors when you have a large number of predictors, etc. on Thursday. So be sure to read the reading for that. All right.